Welcome to the fourth day of presentation of the September session of the CECAM workshop, Advances in Electrostatic Calculations, the Road Towards the Exascale. The speakers of today are Dr. Benjamin Stamm and Dr. Laura Grigori. The first speaker of today is Ben Stamm. He got his PhD in applied mathematics from APFL in 2008. Then he became a postdoctoral researcher at the Division of Applied Mathematics at Brown University. And then he joined the mathematics department of UC Berkeley in 2010 as a Charles Murray visiting assistant professor. In 2012, he became assistant professor at Sorbonne University. As of 2016, he's professor at the RWTH Aachen University. His research interests are the discretization of PDEs and in particular eigenvalue problems with interdisciplinary application in theoretical chemistry as well as aspects of reduced order modeling. Ben, thank you for being here.
Okay, thank you, Walter, for this nice introduction. And I hope you see now the screen in full screen.
Yes.
You can hear my voice?
Yes.
Okay, perfect. So thank you. Thank the organizers for giving me the opportunity to present here my work. And I think it is a very good occasion to give at this point for this audience an overview. I won't go into details, but give the big picture about the numerical methods that we were developing in the, let's say, past 8 years. All right, so it's not a single work, it's a whole team behind, and I will represent here this team, and it's a joint activity between chemistry and mathematics. So this makes this adventure so extraordinary in my point of view, because it's very enriching. You can learn from chemists, and the chemists hopefully can learn from the mathematicians. And so I will speak about existing or domain decomposition methods based for different kind of existing solvation models like the COSMO, PCM, linearized Poisson-Boltzmann model, and some aspects on molecular surfaces. And yeah, so as I said, this is a joint work between chemistry and mathematics, and this all started with some initial work on the COSMO method. And yeah, so here's, let's say, some historical perspective of the domain decomposition family. So we started in 2013 about the COSMO and the COSMO forces. And then at some point afterwards, we published some work on the so-called polarizable continuum model, the PCM model, and published or implemented the force calculations in the upcoming year. And we also did some work I will present briefly at the end of this talk on the mathematical analysis of different surfaces, which is a key concept in solvation models. Also, we worked on the linearized Poisson-Boltzmann equation and the PCM model with varying the dielectric constant. So in the pipeline so far is that we're missing the forces for the linearized Poisson-Boltzmann model and a linear scaling implementation of the DDPCM. And the goal is to implement this everything in one common library that should be called DDX. Okay, so some note. This is an overview talk, as I already said. I will give a brief picture about the domain decomposition paradigm. I will try to convey the messages in terms of concepts and not technical or mathematical details, except two exceptions, namely some technical tools that is somehow the two tools we constantly use in the discretization of the underlying equations. And they can somehow be put in abstract way, and I will present those two tools. And after that, I will go then through the different models and tell you how we use those two tools. So this talk is about the design of accurate and efficient numerical methods and not about the application itself. We have seen talks about the application. For instance, Filippo Liparini gave one talk on applications. On new solvation models, we have seen also their talks on non-equilibrium effects. There was one talk by John Herbert on this topic. And so this is for existing solvation models, how you discretize and solve these equations efficiently and accurately. So what means efficiently and accurately? So if you look at an abstract view of the modeling cycle, you first have to establish a model, a set of equations, of relations, possibly in form of a partial differential equation or an integral equation. And the unknown might belong to infinite or finite solution space. Think about a polarizable force field. Then you have, for each atomic side, you have an induced dipole, and this then belongs to a finite dimensional solution space. But if you have more a model in the distributional sense, where your unknowns are potentials or densities, then these are functions, and functions, they belong to an infinite dimensional solution space. And in this case, you need to first discretize the equations. So you need to introduce, let's say, a possible basis set and project everything onto this space spanned by the basis set, and then you can implement it on the computer. And so this notion of numerical method transforms the infinite dimensional problem in a finite set of linear or nonlinear equations for a finite number of unknowns. Okay, these degrees of freedom. And this model you can then implement on a computer and possibly solve. But even this equation you cannot solve to infinite accuracy, because you might have a iterative solver to solve a linear system like the GMRS or precondition gradient conjugate, and you end up at some point also with a non-exact solution in terms of linear algebra error. Ideally, each step, so modeling, numerical method, and numerical solution, introduces an error that ideally is of equal order. Why should you have a very high accuracy in discretization if your model itself is garbage? You wish, on the wish list, you wish to have a systematic improvability of the error of the numerical method and solution, so that it can be systematically improved to any desired accuracy. So the accuracy is under the control of the user. This is for the numerical methods and numerical solution. This is more or less achievable, not always the case, though. But ideally, you want this also for the model. And especially in, let's say, in continuum solvation models, this is not really the case. You accept the model and then you discretize. But for instance, if you are working post-Hartley-Fock methods, then while you can include more excitations, etc., and you can systematically improve your model typically. On the other hand, like a theory like DFT, it is not, because you kind of married with exchange correlation functional. Of course, you can improve that through the Jacobs ladder, but this at some point you pay in terms of very high computational cost. All right. So the modeling for this audience, I don't think I need a very precise introduction to the continuum solvation models, but nevertheless, let me just remind you a few concepts. So this is a picture from my collaborators at the University of Pisa in the group of Benedetta Menucci and Filippo Liparini, and they study a protein like this, which is the light harvesting complex number 2. And if you put this in a lipid membrane and put some solvent molecules around, you end up easily with a million degrees or a million MM atoms. Okay, and this is of course a huge numerical challenge, but they want to study some quantum effects of some charge transfer at some specific site. So at some point, somewhere in this model, you need to allow a quantum mechanical description of your model. And so you cannot just truncate, let's say, your protein and just cut things out, because the underlying problem, and this is well known to the entire audience here, is electrostatics, and electrostatics is long range. So many relevant applications in chemistry are not in gas phase or isolated systems. So you cannot just ignore the effect of the environment, but you have to account the environment, the effect of the environment onto your quantum mechanical core Hamiltonian. And so here in this simplified setting, we consider a solute in a solvent. There are more refined multi-scale models like the one Filippo was introducing, a QM-MM continuum. So you have 3 layers of theory. Here, for sake of simplicity, I consider a solvent that is we'll see, I have a certain continuum description, and a solute. Okay, and the effect we want to take into account that matches quite well. The topic of this seminar is the polarization between the 2 systems, the solute and the solvent, through electrostatics polarization. But if you go, for instance, to the response theory on your quantum mechanical Hamiltonian, then you see explicit contributions from the environment in the QM Hamiltonian. So this polarization is really fundamental in order to capture the correct chemistry of physics. Oh, that was actually here. Okay, so. All right, this is a well-known example here. You take one molecule, you put it in different liquids, it appears in different colors. So it's fundamental somehow, despite the absorption happens here in this molecule, the environment has a fundamental impact on basic properties like the spectrum of this molecule, so it appears in different colors. All right, so let me here introduce the continuum solvation model. So we have a solute here just depicted by these 4 atoms here, and we have some solvent around here depicted by these blue ones with possibly some free floating ions. And the first you have to do, or one does actually, is to define a hollow cavity, omega, where we say, okay, here the solvent cannot access. And then you replace the explicit description of the solvent on the outside of this cavity by a continuum level of theory. So here, let's suppose we are given some charge density here, rho. We want to solve the electrostatics problem in the presence of this medium on the outside. And then if you couple this with a true quantum Hamiltonian description, of course, you have to iterate through a self-consistent field iteration between the charge here and the environment. And that's the way you get mutual polarization. Or if you have here some induced dipoles, so you have also some flexibility to catch polarization, induced polarization, then you have somehow to iterate between the equations for the induced dipoles and the environment on the outside. Okay, so from my perspective, from perspective modeling, you have, or there are 2 main ingredients. First is the cavity of the solute. So the region where the solvent cannot access. There are different ways, we're going to discuss them. And the second one are the properties of the continuum. So the governing equations like depicted here. So what kind of partial differential equation you have to solve, or what kind of set of equation you have to solve in order to model the interaction between the solute and the environment. Okay, so let us quickly address the notion of cavity. So surprisingly, the definition often is only given by words in the literature, like the SES is given or is described as taking a probe ball and rolling it over the van der Waals cavity. Yeah, so this being said, the van der Waals cavity is simply the union of spheres or balls centered around each nuclei. If you want also to take into account the character of the solvent, because the van der Waals radii, they are always the same, no matter what kind of solvent you have on the outside, you can define the so-called solvent accessible surface, and then you add some additional radius that is somehow accounting for the nature of the solvent. So here you get this black surface here. that is topologically or mathematically the same like the van der Waals. You just have slightly bigger radii, but it's also union of balls. The SES is somehow the region of or the boundary of the region where the probe cannot access if it's rolling over this van der Waals surface. At the end, I will give a mathematical sound definition of that surface. Yeah, but for now we accept this definition by words. But you can also define different kind of cavities, so isodensity. So you take somehow the outcome of your electronic structure calculation. You have a electronic density, and you put a threshold of 10 to the -3 that gives you a boundary where you say, okay, this is molecule or this is solvent. However, when it comes to differentiating in order to access forces, for instance, this kind of cavity, it goes through you need to account the derivative of the electronic density. So it enters also the DFT or whatever model you have on the quantum mechanical side, and this can be quite technical. Or you just say, I take a union of Gaussian type functions centered at each atom here, and then I take isolines of this sum of Gaussians. Is also a valid choice. All right, what is polarization? So very briefly, because this should be familiar here. So the solvent molecules have the capability to induce a dipole, and this is called polarization. And this is reflected by the macroscopic dielectric permittivity. So we define a function that inside the solute is equal to 1, because that model's void. And on the outside is some constant here that is epsilon s, which is the bulk dielectric permittivity of the solvent you're considering. So somehow the geometry of your solute molecule is embedded in the notion of this cavity and thus in this function. Then you solve a generalized electrostatics problem where rho is the given charge distribution. This can be sum of point charges if you only have a molecular mechanical description of your solute, or it can be the nuclear charges plus an electronic density, and if you want to couple this with a quantum mechanical model. You solve this is this function that jumps, and then you compute the electrostatic energy. That's the task. However, this notion of dielectric permittivity is not so trivial, because you have in different time scales, you have different notions. So if you make it frequency depending, you see electronics polarization, atomic polarization, dipolar polarization, etc. And I think John Herbert's talk also was putting light into that. Here we just accept that it is given as a constant, but the picture might not be as simple as that from a chemical point of view. All right, screening is another effect. So we speak about polarization and screening. Screening is if the ionic solvents, or if ionic solvents are considered, and the ions are represented in the solvent region also by a continuum ansatz. So you do not model the exact location of some explicit ions, but say I have in a certain area a certain density of ions. And you make a equilibrium assumption that the ions, they behave up to a Boltzmann distribution here, where Ci infinity is some concentration, Zi is the charge, and you see here this is nonlinear PD, because in order to have the thermal equilibrium of the ionic densities, you need to know the potential, but you actually are you're computing the potential. What you can do if you do linearize this is in a particular case when the charges are opposite. If you have always a plus and a minus ion, then you have here a plus and a -1. And in addition, if you make a certain low potential assumption, you get here 2 exponential terms that you can combine together in a sine hyperbolicus, that then you also do a Taylor approximation of first order, and you get a linear term in V from here, and you get the so-called linearized Poisson-Boltzmann equation, which will be subject of the next 2 sessions, 2 talks, I think. Well, not the one after that, but in the next session. So kappa here is equals, this is actually a typo, this should be equal to 0 in the molecule, and is some modification so that we can divide by epsilon s the equation. You have here this term here plus the kappa s, that is the so-called Debye-Hückel screening constant. Okay, once you solve this, then you compute the electrostatic energy. All right. So a note on ionic solutions, the effect of screening by ions is that the potential decays exponentially with increasing distance to the solute-solvent interface. So here the black is a typical exponential damping, and this, or Iwakawa potential, and this is just this, the long range 1/x. And so from a computational point of view, the ionic solvent is much easier because you can put your things in a box, and at a certain distance to your interface, you can safely assume that the potential needs to be 0, which you cannot do in a pure electrostatic without damping scenario. Okay, or if you do so, you will obtain huge errors in your model. So that's why, especially for non-screening cases, methods based on integral representations covering the whole unbounded domain are very popular. All right, so here a quick overview in the continuous case. So you have, let's say, this generic model where we have possible ionic concentration, you have some dielectric constant, and then you can make the limit as kappa s. So say there's no screening, then you go to what I call polarizable continuum, or what is known in the community as polarizable continuum model. Yeah, is this one with kappa s equal to 0. And you can even further simplify and say, well, the polarity, the dielectric permittivity of a solvent can be highly polar. So epsilon s can be assumed to be very high. Water is 78 point something at room temperature. So let us take it to infinity. Okay. The model is crude. Why not take it crude gas for the epsilon s? And this is the so-called Cosmo model. Okay, now I come to this part, which I said there are a little bit technical, but these are fundamental concepts if you want to understand our domain decomposition methods. So one is the domain decomposition method itself, and the second is a localization strategy for integral equations. All right, so trivial example of a domain decomposition method that exists since a long time in mathematics and dates back to Schwarz in the 19th century, where he wanted to solve something like a problem like this with power series. So in our example, we want to find a harmonic function, and harmonic functions in 1D, they are usually straight lines with boundary conditions 0.5 and 1. Well, we want to solve it now on subdomains. And what you can do is to say, I have a subdomain from 0 to 0.75. And I solve here, I'm looking at the iteration k at a harmonic function that has here the exact boundary condition. And on the right-hand side, I don't know what it should be, but let's just take the iteration of the solution on the other subdomain at the previous guess. And you do the same for this one. In pictures, if you start, you don't know anything better than putting a 0 here and a 0 here. You draw a straight line because that's the unique solution to the problem in 1D. And then you see the second guess for the problem on the right. You take this boundary condition, and here you have the exact one, and vice versa. And you see this is a process that converges. And this is what we're going to use on a in the framework of atomistic geometries. So how do we use that? So the main idea is to divide your computation domain into overlapping or non-overlapping subdomains. That's generally for domain decomposition methods. In the case of molecular cavity, because you want to write them as a union of balls, you have only overlapping subdomains. And then the goal is to solve an equation on each of the subdomain and couple them by suitable boundary condition. So in the case of the Cosmo equations, which can be written like here, so you look again for harmonic functions. So that means that the Laplace operator of W needs to be 0 in the overall cavity, and you want to prescribe some fixed value on the boundary of the cavity. So then domain decomposition for this kind of geometry simply is realizing that the cavity is a union of balls and that you can decouple them and write for each of the ball an individual problem. In this case, we are now on this on the ball, and we have some boundary condition. Of course, the boundary condition, if it happens to be here on the blue part that is exposed to the solvent, you can simply take -phi, the exact boundary condition. Whenever it's in here, you say, well, it should, we take the solution of the previous iteration for the green one. Or in here, we take 1/2 of the green, 1/2 of this brownish one, etc., and you iterate until convergence. So in practice, this looks then like this. In the beginning, you have garbage, and then you slowly, or you converge to the solution where all the different local problems are coupled in a self-consistent way. Okay, so now you reduce your problem to solve problems on a simple ball, okay? Because we couple them through boundary conditions, so we only need to deal how to solve the problem on a simple ball. And the ingredients for the discretization are spherical harmonics. And for numerical integration, we have, or we will use the Lebedev quadrature. In a nutshell, if you want to solve the problem that in the unit ball, you want to solve, or you want to represent a function that is harmonic, you can easily express this with a series representation of spherical harmonics in the angular degrees of freedom times the distance to the center to the power of L. So in practice, when you then want to solve these problems in one of the atomic balls, while you need to truncate because you need to have a finite dimensional number of degrees of freedom, plus you shift them so they are centered at the atomic sites, and that's your ansatz, and you want to determine these coefficients through satisfying the equations. In general, if you have any kind of operator here, that is for Cosmo or PCM is something like minus the Laplace, and for the linearized Boltzmann equation, you have minus Laplace plus kappa square. For a given boundary condition here, you can ask yourself, or we will frequently use the notion of Dirichlet to Neumann operator. What is this? I explain in a minute, but let me just mention here that the omega is a union of spheres considered here. So if you have to solve this problem, the Dirichlet to Neumann operator is for given function here, we want to solve this problem, and as an output, give the normal gradient on the interface. So this means, given this, you have to solve this equation and then access the normal gradient and give this back. And this operator is called Dirichlet to Neumann. So why do I stress this? A, because this frequently appears in integral equation formalism of these electrostatic problems. And second, we can solve this problem very efficiently with the domain decomposition strategy. For given G, you do exactly like I explained in the Cosmo equation, and then at the end, you just give back the value of the normal gradients. Okay, that was tool number one. Tool number two is the localization of integral equations. And so very generically, I take here an integral operator that acts on a given function f, and the image for a given s is the convolution over the outside of the molecule or the cavity, so this red surface, of s f at s prime times some kernel function. This depends on the operator itself, what kind of kernel function you have, but you think about the Green's function of the Laplace equation in order to define the so-called single layer boundary operator, or its derivative to define the double layer boundary operator. Okay, how you can do this in a domain decomposition way? Well, first thing we did is we define local functions for each atom, and we just give them the value they have on the outer part of the boundary, but extended by 0 on the inside. Okay. Then what you can use is the following fact that if we have here the definition of this operator, this is per se only an integral over the outside of the cavity. If you plug in the fj's, you can also easily integrate in the inside, because at this part of the boundary, the function itself is 0. But what you gain, on the other hand, is that this integral can be written as a sum over integrals over balls or spheres. So you can write this as a sum of local contributions. Secondly, at the point when we're going to discretize this densities here with spherical harmonics, you have here a spherical harmonic times some integral kernel. And this very often, or in the cases we're considering, you can naturally link to this to the fast multipole method. That means you can, these terms, local terms, interpret as multipolar expansions in the center of each atomic site, and then run an FMM to evaluate the potential for given multipolar expansions on each atomic site. Okay, so now let's assume in an abstract way we have an integral equation of this form with, for a given j here, g, we want to find a density f such that f plus this operator applied to f is equal to g on the outside, on the outer surface. So this appears, for instance, in the DDPCM equations. And so what you can do is first to localize your equation. So we introduce here the characteristic function of a certain region. So we localize it here and say when this is equal to 1 whenever we are on the outer surface. So when S is on the outer surface, we have this original equation. When S is somewhere on the inside, like here, well, this term drops and this term drops, and we just say that F should be equal to 0. This is exactly what we wanted, or we ask for. And then we do nothing else than multiplying on each of the sphere by a spherical harmonics and integrate it over. And for the Fn, we do a finite truncation of spherical harmonics. And then if you do the math, you end up with a linear system of equations that you can solve. But the trick was to extend the unknowns inside and write everything as a sum of atomic contributions. All right, this was the tool number 2. So let us revisit very quickly the Cosmo. I want just to mention here that you can view Cosmo equation from 2 different angles. From a partial differential equation point of view, PD point of view, where you have this problem, or from an integral equation point of view, where you have an integral operator, V, that is the convolution of the Green's function over the molecular surface. And this is an invertible operator, and you have to solve this, invert this operator to access the sigma. Once you have solved for the sigma, you apply it here in the exactly same formula here, but the tiny difference is that X now lies anywhere in the cavity, and here the S is on the surface. So you might ask your question, why do we distinguish between this and that operator? The trick is that this operator, if you restrict the S only on the sphere, this is an invertible operator. And this is key, of course, if you want to invert this set of equations. All right, I'm not spending much time. I'm running a bit out of time, so I'm not going through the state of the art about continuous surface charge, etc. I'm skipping here. I want to speak about other things. So I just want to mention that the DD-Cosmo algorithm proved to be much faster than what was the state of the art, or is the state of the art, for instance, in Gaussian. And yeah, this has been reported in the article. And the key is the linear scaling. So here's the elapsed time for different compounds with different numbers of atoms, and the solution of this linear system and the joint linear system, because we want to access the forces and the force computation, they all scale linearly. And one of the keys here is because the matrix entries of your solution matrix are very sparse, because two blocks have non-zero entries, like for instance here, only if the two atoms do not intersect. Okay. All right, so the DD family, on one side we have some functions with a sharp interface, where we have a piecewise function that has epsilon s equals to, or the epsilon function is some finite value here, but it's constant and one inside. But we also have a version where it varies from the inside to the outside in a continuous manner. I will quickly address it towards the end. And yeah, so we have this DDLPB or PB. You can go to make kappa s equals to 0. So here you find the limit of the DD PCM result. Or you can go this way to increase the kappa s and you find the DD Cosmo result. Or you go from here, from DD PCM, and you scale up the dielectric constant, and then you end up with the same result between DD PCM and DD Cosmo. So there's a whole family, and they talk to each other in a consistent way. Okay, so one slide about DD PCM, because I did already the technical stuff before. So if you go to this Menucci-Kances paper from the 90s, you have this integral equation formalism PCM, and you find there an equation of this form where you have two integral operators. And as you would do, for instance, with solving LU factorization, you can do this in two different steps. You first call this epsilon phi epsilon, and you solve here for the phi epsilon. And then you plug it in the second equation, and you do this. The catch here is that the second equation is exactly the DD Cosmo part. This has already been discussed. We know how to solve it. So what is effectively new is just this first part. And this R epsilon is exactly how I describe with tool number 2, an integral operator that can be written as identity plus some compact operator. And where we do this trick as explained. One note though, if epsilon s goes to infinity, then this operator becomes equal to that one. And since the operator is still invertible for infinity, phi epsilon equals to phi, and you can skip the first part and directly solve DD Cosmo. So that gives you the consistent limit when epsilon s goes to infinity. So some very quick numbers. So here we compare with the continuous surface charge implementation in Gaussian, where there are different versions. So naive and cube implementation with a direct solver for the linear system, then some more, some better and squared implementation here. And this is the DD-PCM implementation that you see here. Scales much better, but this is still with non-FMM accelerated operators. So this will scale eventually also quadratically. And if you see here very well, this the Cosmo contribution is much smaller and different in scaling than the first equation. And so it's ongoing work to have an FMM-based DDPCM. So this part that is expensive here, we tackle them and want to bring it down to the Cosmo equation to have it linearly scaling. All right, the DDLPB is a bit different. So Walter, how much time do I have?
I'd say 10, at least 10 minutes.
Okay, good. Yeah, very good. So here we see the original problem. I split between the problem in the cavity and on the outside. It's a problem of on an unbounded domain. There is a mathematical trick to bring it down to have an equivalent formulation, but only with problems in the cavity. The price you have to pay is that you have a non-local boundary condition. Okay, so this is a convolution over the molecular surface. But I already explained you how we do it with this equal to 0 on the inside and write it as a sum of atomic contributions. So we have all the tools in order to do that. So here is a very, let's say, illustrative way how we solve the equation. So you have this coupling condition here. And if you have a gas omega, okay, you can try to solve these problems on the left and the right. These are so-called Dirichlet to Neumann operators. That's why I stress this fact so much, that you need to solve. We can, for this, use the domain decomposition paradigm. What we need is to have the normal gradient on the surface to report back for different kind of PDs on the left and the right. To do this, make this convolution over the surface, and then we have a new gas and you iterate like this. This is DD Cosmo, we know how to do it, and this can also be done just with a different way of solving the problems on an individual ball by using Bessel functions, modified Bessel functions, and not just polynomial powers of R. All right, so here's a quick comparison between one of the state of the arts, which is the APBS. So what you see, the essential thing that you can see, so here is the solvation energy, but here's the relative error that we have, because it is a spectral method, we have very fast or exponential convergence in the degrees of freedom, whereas any finite element or finite difference approach is first order, and the mesh is not adapted to the geometry. So you have a geometry error of order 1, and you see this. So it's particularly if you go to couplings with quantum mechanical Hamiltonians, where you wish to have a better accuracy than 10 to the -2 for your solvation models, you can easily access them with DDLPB. So here is a study on the computational cost. So we compare here two scenarios in terms of degrees of freedom. So this is DDLPB, on the bottom is APBS, where we have similar relative accuracy, and the runtime you see here, as well as the memory, are in favor of DDLPB. So this is on a molecular compound having 141 atoms. Okay, I'm sorry, I'm running here a bit because this is just overview over the different models without going into depth about more numerical results, etc. So we also came up with a model or a numerical method to capture not a piecewise constant dialectic function, but actually something that is varying in a smooth way between the SES, this what seems to be the smoother version, to the SAS, by just having here some switching function. And the picture is like before. We don't go into details, but you write this again as two PDs or two equations inside the cavity, some non-local coupling conditions, You have here this integral equation. You have here this Dirichlet to Neumann problems that you solve in the domain decomposition way. Now here you have this epsilon that is varying in space, and this makes a big difference. This is what you should retain here. But once you solve this in the DD fashion, you report your normal gradients back and you iterate. So what is now new is the domain decomposition, because you have in the very simple case something like this, and you don't have a homogeneous dielectric permittivity inside your cavity. On the outside, you assume you do have. But also here, why not do domain decomposition? It's just that we have to solve 3D problems here and one here, and we can just exchange the boundary condition and iterate and apply the same concept. So yeah, one matrix vector multiplication can then be obtained as a sequence of local problems, each posed in a ball, which are coupled by local and global conditions. This approach does not rely on the SES-like cavity. Also, isodensity approach or Gaussian type surfaces can be used. So this has been published in a math paper, and I see somehow that is not came to the chemistry community yet, because it was probably published in the math journal. But so that's why I used the occasion to make here some advertisement for that. All right, and a simple case just to illustrate how you can have non-trivial topology changes. So if this kind of breaks apart in the SES, we don't see any fluctuations, unexpected fluctuations in the energy, as well as if you go from two double junction to a triple intersection. Yeah, okay. So the final words are on the STS. So I promised you to give a rigorous definition on of the SES in the beginning. So at the origin, and this is my, so Walter, this is my final part, at the origin is the so-called sign distance function to the SAS. So this is the red one. Okay, so this is a function that at any point, it reports you the distance to the surface. In the outside is positive, as you can see. On the inside is negative. Okay? By a trivial statement, the SES can be defined as all x's such that the distance to the SES is 0. This is a trivial statement, but just in order to get used to this notation, what you can now do is to say, I take the level set of minus RP. And this is exactly all blue points. These are all points that have a distance to the SES of minus RP. Okay, that means you take this sign distance function and you cut it at a level of minus RP, and the intersection is this blue curve here. And so also you have this correspondence here between balls and balls of arcs and toroidal patches and triple intersection and these concave patches. This is known since a long time, since the seminal work of Goloni. What we introduced is some new partition of the Roroni diagram, and in 3D it looks like this. We partition the inside, whether it closest point on the SAS is on a surface patch, on an intersection arc like these yellow ones, or intersection point. And with that, we can carry out the singularity analysis for the SES, because there are quite a few singularities. For instance, this point has an infinite number of closest points on the SES, which is the intersection circle of the two SAS balls that you have to imagine. There's slightly bigger balls that intersect. Or here, these singularities have exactly two closest points, one this top intersection point on the one on the bottom, etc. And you think these are just occasional appearing in the real molecule. You're wrong, because here all green patches correspond to singularities. So this SES is not that smooth as usually known. And yeah, so here are the two corresponding papers. We have some elementary MATLAB code if you want to test, but it's not efficient, not at all. It is just some code in order to check our stuff. And you can even output some file where you can then 3D print your favorite molecule. All right, so I come to the conclusion. We have seen a short glimpse on the mathematical tools that are used to derive efficient and accurate solvers for several continuum solvation models. The two main ingredients are the use of overlapping domain decomposition methods, and the second, the localization strategies of integral equations. This allows the use of localized basis functions in form of spherical harmonics, something like atomic orbitals. You have a set of degrees of freedom for each atom. And this also simplifies to some extent the derivation of gradients, because basis functions are attached to atomic positions. And this leads to efficient numerical methods. We are now in the process of developing a library that is called DDX, where all these methods should be unified and implemented with one simple or one interface, allowing for coupling with quantum mechanical or molecular mechanical or QMM-based methods. And we also plan an interface with Psi4. So thank you for attention, and here are a few references.
Thank you very much, Ben, for your presentation. Waiting for people in case they have a question. I have one question myself. You compare your approach with APBS in terms of performance efficiency. But if I got it correctly, your approach is limited to the linear Poisson-Boltzmann, in case it is applied to. So have you tried comparing with some boundary element method, which from some point of view should be more closer in spirit to what you are doing?
Yes, so in this paper, we also compared with to TABI-BB. And we see that we're quite comparable, I would say equally up. However, we still have to implement a fast multiple type strategy. There's a lot of human work involved to do the forces, etc. So we are advancing quite slowly, but this is planned at some point. The reason why maybe a comparison with TABI-BB, or I didn't put it here, TABI-BB as we used it is on the SES and we are on the SAS. So we cannot quantitatively compare the results and draw some meaningful conclusions. But yeah, the tree code accelerated TABI-BB, etc. We're in similar range. The exact numbers, I refer to this paper. You can look it up, and I hope we were kind of did a fair comparison.
Okay. Okay, thank you. Is there any more? Yeah, go ahead.
Yeah, thank you for the presentation. I have about two questions. So in the beginning, you mentioned the control of errors in each single step, or that you would like to have the same error more or less in each ingredient of the methods. So since you are solving the linearized Poisson-Boltzmann equation, I wonder, do you actually have a method or a measure to validate the linearized approach for the Poisson-Boltzmann, and how do you do it in the calculation?
The honest answer is I don't think one has, a very clear way to, in general, not only Poisson-Boltzmann versus nonlinear Poisson-Boltzmann. Of course, if you could solve the nonlinear one, you can compare to the linear one. But in general, in this, in this approach, what is the truth, right? And so the truth might be some experimental result about some spectroscopy of the absorption spectrum of ultraviolet light. But there, we did one work, and so my collaborator were quite happy when we added Cosmo to the vacuum Hamiltonian, the spectrum was shifting in the right direction, but by no means you could see that the spectra were quite similar. So I think there's a huge gap, but also a lot of things to be done to kind of have some systematic ways to improve the models.
Yeah, is that the goal of you or your group activities to do the step to the nonlinear Poisson-Boltzmann equation, because that would be the way to solve it correctly.
So there's one catch with integral equations. With integral equations, they do not allow the nonlinear Poisson-Boltzmann, because you need a linear PD operator with a constant Debye-Hückel constant, or at least a linear PD operator. And then you have a Green's kernel, and then you can apply all this potential theory where integral equations are used. And we rely on this methodology. It is not straightforward to come up, or I haven't seen integral equation-based formulations for the nonlinear case. My PhD student, Chayu Kwan, who was the main driver of this work, he once thought about how to do it, but we didn't come up with a satisfactory answer. Yeah, this seems to be a limitation of the approach, where, let's say, PD-based, like finite element of finite difference, seem to be able to handle this.
Yeah, I have a second question. Since you didn't mention at all parallelization of this method, I wonder whether you can link libraries of ODE solvers or PDB solvers to your method, or are you on the way to include it to some libraries, so that it also has a perspective on efficiency on modern computer architectures? And
so I see your point. So it depends really much, and here is a bit, because we have a method that is suitable for, let's say, biophysics or biochemical application and quantum chemical applications, and the settings are quite different. For instance, polarization is not that much of a topic in theoretical chemistry as used, let's say, by my collaborators. The limiting factor is more kind of memory, and you need to have a good machine with a lot of memory. And the quantum mechanical problem is so expensive that you first parallelize this one, and you put less emphasis on the continuum solvation. If you go to something, we have some work on coupling polarizable force fields like amoeba with DD Cosmo. Of course, then the entire complexity is shifted to the continuum solvation model. And for DD Cosmo, we have some Mpi implementation, and we showed quite good scalability. I don't think I have the figures somewhere saved here. For the remaining stuff, we didn't have time yet to think about this. Yeah, we did DD Cosmo, and the others, yeah, I mean, I have a long wish list, but only limited human power. And there's another problem. I'm in the mathematics, so I need, I have to graduate PhD students in mathematics and postdocs. I should give them a career perspective and just let them implement an existing code with new developments in the MPI, etc. It's critical. And I don't know, I would love to have, like in France, a research engineer that do this kind of stuff. Or maybe in Jülich you have more human resources for such kind of jobs. But yeah, that's one thing I see as kind of a limiting factor here in the development.
Okay. Thank you.
Let me just browse if I have the MPI. So here, here is the scalability of the MPI implementation. of course, the larger the protein you're modeling, the better scalability you have, because at some point you're just communicating and not computing anymore. And the problem here is as well that, you know, it's not that big, the molecule, but you do maybe 1 million time steps, right? You have the sampling in time and let's say small problems. So, yeah.
Okay, thank you.
Okay. If there are no more questions, then let me thank again the first speaker of today, Dr. Benjamin Stamm.